Okay, so we just found the surface area of this red cube to be 6e squared. But we're multiplying the edge length by x. And so this new side length is x times e. And so now the new surface area, this would be xe times xe. So xe squared is the area of the square, and there's 6 of them. So we would have 6 of the x times e's squared. Now this simplifies because each one of these is being raised to the power of 2 to 6x squared e squared. Now in order to compare it to our original surface area of 6e squared, we're going to use what's called the commutative property, which means the order of this multiplication does not matter. So I'm going to move the x squared up front and show that it's x squared times the original surface area of 6e squared. So what happens to the surface area of a cube? When the length of the edge is multiplied by a factor of x, the surface area is multiplied by x squared. So that is your answer to number 4. What happens to the surface area of a cube when the length of the edge is multiplied by a factor of x? The surface area is multiplied by x squared. Question 5 is looking at volume. So again, our original cube has a length of e, and so the volume would be e times e times e, length times width times height, which is e cubed. If we multiplied the edge length by x, then our new volume would be xe times xe times xe, which is xe to the third power. So remember, that's the same thing as x to the third times e to the third. So we can see our original volume, e to the third, is being multiplied by x to the third. So what happens to the volume of a cube when the length of the edge is multiplied by a factor of x? The volume is multiplied by x cubed. The volume is multiplied by x cubed. So questions 6 and 7 in your notes, it says, how are the volumes of two similar solids related? So what you need to really understand is it all depends on what your linear change is. If you're doubling the linear dimensions, then you would do that change, which is doubling is 2, and to find the new volume, you would cube that change. So 2 to the third power is 8. So your volumes would change by a factor of 8. So you take your linear ratio and you cube it. How are the surface areas of two general similar solids related? Well, surface area, you are going to square that linear ratio. So if you're doubling the side length, 2 to the second power is 4. Your surface area would quadruple. That's the relationship we're looking at. So let's look at that in an example here on question 8 in your notes. So it says this is not really an example. We'll get to an example number 9. Question 8 is just wanting to know, can we solve this puzzle? So I'll bring it here where I can drag these over here. So it says, can you solve the puzzle to summarize what we have learned? Drag the tiles to describe the dimensional change between two similar solids that have a scale factor of x. So this scale factor is a linear ratio. The linear scale factor is x. So that means the ratio of any corresponding edges of the two similar solids, the edges, the length, the width, the height, those are linear dimensions. So the ratio of them would also be x. So we know if our perimeters have a ratio of 2 to 1, then that means the lengths have a ratio of 2 to 1. The widths have a ratio of 2 to 1. The heights have a ratio of 2 to 1. All the linear dimensions have the same ratio if they're similar solids. It says the ratio of the perimeters would have what scale factor? Well, perimeter's still linear, right? So it would still have that same scale factor of x. Now the next one is the ratio of areas. Areas is not linear. Area is quadratic, right? That is always going to have squared units. So we need to take the scale factor for linear dimensions and square it. X squared would be the ratio of the areas. Surface area is also squared units. So we're also going to take that linear scale factor and square it for surface area. Volume is cubic units. So we're going to take that scale factor and cube it. So we would have x cubed as our ratio for the volumes. So there are our answers for number 8. So now let's look at the examples in numbers 9 and 10. Let's put some numbers to these. So the first thing we're going to do is find the surface area of this rectangular prism. They've given us the net there that makes that a little bit easier to kind of visualize. So we have 1, 2, 3, 4 rectangles that are 2 by 3. So 2 times 3 is 6, and we have 4 of them, so that's 24. We have 2 that are 2 by 2. 2 times 2 is 4. 4 plus 4 is 8. So we have 24 plus 8, which has a total surface area of 32. So our surface area is 32. We're going to find out what the new surface area is going to be if we change the linear dimensions with this scale factor. So remember, we're not just going to take 32 and multiply it by this scale factor. That's not what we're doing. This is a linear scale factor, and we're trying to find a squared result. So in order to find our surface area, we're going to have to take this linear change and square it. So you're going to have to take 1.5 and square it. And so 1.5 squared is 2.25. That's what we have to multiply by our scale factor. So 2.25 times 32 gives me 72. That would be my new surface area. So again, you're going to take your linear change and square it. So if our scale factor is 2, of course we know 2 squared is 4. So we're going to multiply 4 times 32, not 2 times 32. So our new scale factor, our new surface area is 128. So hopefully you see what we're doing here. We're taking the scale factor and squaring it. 2.5 squared is 6.25. And then multiplying it by the surface area of 32. So we get 200. And finally, 3 squared is 9. 9 times 32 is 288, would be our new surface area. Okay, so that's surface area. Now let's look at volume. So to find the volume of a rectangular prism, remember it's just length times width times height. And so we would have 2 times 3 times 2. Okay, so we have a width of 2, a length of 3, and a height of 2. 2 times 2 is 4, times 3 is 12. So the volume of that rectangular prism is 12 cubic units. You could find the area of the base, which is 2 times 3, which is 6. Multiply it by the height, 6 times 2 is 12. So to find these new volumes with these linear scale factors, remember you're not just multiplying the scale factor times the volume. You have to take the linear scale factor and cube it this time to know what to multiply by to get the new volume. So we're going to start with the 1.5 scale factor. We're not squaring it this time. We're cubing it. So we're raising it with that caret key to the third power. 1.5 to the third power is 3.375. That's what I'm going to multiply by my volume of 12. And that gives me 40.5 for my new volume. So the next time my scale factor is 2, I'm going to cube 2, which is 8, and multiply 8 by my volume of 12. So my new volume is 96. So hopefully you see the pattern here. 2.5 to the third power is 15.625. That's what I'm multiplying by 12. 187.5 is my new volume. And 3 cubed is 27 times my volume of 12 gives me a new volume of 324. Whoops. There are your answers to number 10. All right, so remember, perimeter is a one-dimensional measure. Okay, so it's going to have the same scale factor for similar solids as the length does, as the width does, as any other linear one-dimensional measure has. Area is two-dimensional. So to get its scale factor, you have to take your linear one and square it. Volume is a three-dimensional measure, so you have to take your linear ratio and cube it to get its ratio. All right, good luck on your homework.